Now, we need to state that formally too, but in order to move in that direction, we first need to bring in, as I said, another function which will span V 0. So, we need to bring in this idea of spanning. We say a set of functions, we say a set of functions, let us say f 1 to let us say f k and so on, span a linear space if any function in that linear space can be generated by the linear combinations of this set. Now, again there is this subtle distinction between finite linear combinations and infinite linear combinations. I do not wish to dwell on those distinctions at the moment, but what we are saying, what we mean by span. So, when we talk about the span of a set of functions, we are talking about all linear combinations of those functions, and therefore, the set or the space of in fact, the space of functions generated by all linear combinations of that set. So, now we ask a question which should make our life easy. What function, we asked this question before, but now we answer it. What function, suppose we call it phi t and its integer translates span V 0. And the answer is very easy. In fact, if you were to visualize a function which is 1 in the interval from 0 to 1 and 0 else, lo and behold, you have the answer. So, what we are saying is any function in V 0 can be written like this. Summation n over all the integers C n phi t minus n. So, essentially integer translates of phi. And these are the piecewise constants here. Just to fix our ideas, let us take an example here. So, what we are saying is, for example, suppose I have this example of a function in V 0, all right. So, I have 0, 1, 2 and 3 and so on. The value here is, let us say 0.7, the value here is 1.5, the value here between 2 and 3 is 1.3, the value between minus 1 and 0, let us say is 0.2 and so on, then and this could continue. Then this function can be written as dot 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 plus 0.2 times phi t plus 1 plus 0.7 times phi t plus 1.5 times phi t minus 1 plus 1.3 times phi t minus 2 and plus dot 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 and so on. Simple enough, not at all difficult to understand. So, we have this single function phi t whose integer translates span V 0. Now, the subtle point is that if you were to go to any space V m, so the same thing would carry forth. So, it is very easy to see that any space V m can be similarly constructed. In fact, we can be more precise. We can write down V m is essentially the span over all n belonging to z of phi 2 raised to the power of m t minus n. So, just as we looked at the wavelet yesterday and said it is this single function which can allow details to be captured, we now have this function phi t which captures representation at a resolution. It is a very powerful idea if we think about it. If you want to capture information at a resolution, at a certain level of detail, that is all the information up to that resolution, you have the function phi. If you wish to capture the additional information in going from one subspace to the next, you have the function psi, the wavelet. Now, we need to give this function phi t a name. We shall call it a scaling function. Now, of course, here the phi t that I have drawn in this context is the scaling function of the Haar wavelet or the Haar multi-resolution analysis. Now, what is this multi-resolution analysis? I have suddenly brought in this word. So, what is this? Well, this ladder of subspaces that we are talking about here, with these properties, is called a multi-resolution analysis. Or an MRA for brief. Of course, in this case the Haar multi-resolution analysis. Now, what properties? We need to put them down formally once again. We have introduced two of them and one more subtly, but we now need to put down axioms very clearly. So, let us put down what are called the axioms of a multi-resolution analysis. So, the first axiom is, of course, there is a ladder of subspaces of L to R. And we know what that ladder looks like. Such that axiom number 1. Union over all integers closed Vm is equal to L to R. Intersection over all integers Vm is the trivial subspace with only the 0 element. These are not all. Further, there exists a phi t such that V0 is the span over all integer n of phi t minus n. Point 4. In fact, you know, it is not just span, there is something more. These phi t minus n over all n is an orthogonal set. This is a deeper issue here. Now, we will explain in more detail the notion of orthogonality in the next lecture, but for the moment let us be content to put this down as an axiom. Next, if f t belongs to V m, then f 2 raised to the power of m t or 2 raised to the power minus m t belongs to V 0. So, for example, if f t belongs to V 1, then f t by 2 or f 2 raised to the power minus 1 t belongs to V 0 for all m belonging to z. And if f t belongs to V m to V 0, then f t minus n also belongs to V 0 for all integer n. So, these are the axioms of a multi-resolution analysis. That means, this is what constitutes a multi-resolution analysis. And here we have taken the Haar multi-resolution analysis to build the idea up, but the whole abstraction is that we can have several different phi's, and then to end this lecture the corresponding psi's. So, where does the psi come in? It comes in what is called the theorem of multi-resolution analysis. Given these axioms, there exists a psi belonging to L to R, so that psi 2 raised to the power of m t minus n for all integer m and all integer n span L to R. This is a very, very significant idea. In other words, this is exactly what we said yesterday. Take dyadic dilates and translates of the function psi, and you can cover all functions or can go arbitrarily close to any function in L to R as you desire. We have built this idea up from the Haar example, but in the next lecture we shall try and build a little more abstraction into what we have done and proceed further from there. Thank you.
Hello everyone, I am Nikunj Patel. I am TA for this course. You can ask any questions or doubts if you have regarding the material covered in the class.
Hi Nikunj, can you tell us about the analytical proof of ladder of subspaces?
I am not giving the exact proof, but I can prove that V0 is a subset of V1 and you can further extend it by induction. Here we will prove analytically that V0 is a subspace of V1. Let us take any function belong ft that belongs to V0. The basis functions for V0 are phi t minus n for n belongs to Z. Hence, ft can be written as a linear combination of basis functions of V0. The basis functions of V1 are phi 2t minus n belongs to Z. Let us try to write the basis functions of V0, which is phi t, in terms of basis functions of V1. This is phi t, phi t minus n. What are the basis functions of V1? Phi 2t. Let us try to draw how phi 2t minus 2n looks. The phi t will be look like this. Phi 2t minus 2n into n plus 1 by 2. Now let us plot phi 2t minus 2n minus 1. If you derive analytically, then it will be from n plus 1 by 2 to n plus 1. This is nothing but phi t minus n. Hence we can write phi t minus n is equal to phi 2t minus 2n plus phi 2t minus 2n minus 1. We will replace phi t minus n in this equation 1. Then ft is equal to sigma cn phi 2t minus 2n plus phi 2t minus 2n minus 1 is equal to sigma n cn phi 2t minus 2n plus sigma n cn phi 2t minus 2n. Let us call this pt and call this qt. Now since pt is represented as a linear combination of basis functions of V1, we can say that pt belongs to V1. Also qt is represented as a linear combination of basis functions of V1, hence we can also say that qt belongs to V1. Now since ft is a linear combination of two functions which belongs to V1, we can say that linear combination pt and qt belongs to V1. It implies ft belongs to V1. Here we proved that the function f, first we take a function ft that belongs to V0, and analytically we proved that ft also belongs to V1. Hence we can say that V0 is a subspace of V1. you can derive this by induction, the whole ladder of subspaces, which is V0 is a subset of V1 is a subset of V2, so on. Or you can also go backwards like this, V minus 1 and all. That's the proof that of the ladder of subspaces.
I wanted to ask that is L1R a subset of L2R?
It is generally not the case. Means all the functions that belong to L1R does not belongs to L2R. I can give you a counter example of a function which belongs to L1R but does not belongs to L2R. Here I will give a counter example of a function which belongs to L1R but does not belongs to L2R. Let us take ft as 1 upon root t. T belongs to 0 to some constant a. A is some finite constant belongs to R. Now we can say that ft belongs to L1R if and only if L1 norm of ft is finite. We will compute the L1 norm of ft. Is equal to ft dt minus infinity to infinity. Since ft is exists only for 0 to a, we can apply the limit. Is equal to t power minus 1 by 2 plus 1 upon minus 1 by 2 plus 1 0 to a. It is equal to 2 times root t. 0 to a is equal to 2 times root a. Since a is some finite number, L1 norm of ft is a finite. Hence, since a is some finite number, L1 norm of ft is finite. Hence, we can say that ft belongs to L1R. Now we will compute the L2 norm of ft and see that it is finite or infinite. Is equal to square dt power 1 by 2. We will square it on both the sides, then we will take the square root. Integral 1 upon root t 0 to a whole square dt is equal to ln t 0 to a. It is equal to ln a minus ln 0, which is indefinite. Equal to ln e minus ln 0. Now this is indefinite. Hence we can say that L2 norm of ft is not defined. Hence ft does not belongs to L2R. Here we have seen that ft belongs to L1R but it does not belongs to L2R. Hence we can't say in general that L1R is a subspace of L2R. Thank you.